I am Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. We started this series on matrix transformations, and now, after completing the unit on invariant points and lines, here is a test paper for you. We have 3 questions here. The very first question is to find the invariant points of the transformation with the matrix A0, 0 minus A. Question number 2. Find the equation of invariant lines for the following transformation in the xy plane. 3 different questions are there as a part of question number 2. Reflection on the line y equals to minus x. Enlargement centered at origin with scale factor of k, where k is greater than 0. A stretch parallel to y-axis of scale factor of k, where k is greater than 0. You may like to give geometrical interpretation and algebraic proof for your answer in question number 2. Question number 3 here is, find the equation of any invariant line, if any, through the origin of the transformation whose matrix is A equals to 3, 2, minus 1, 0. So the first question is based on finding invariant points. The second one is invariant lines, any line, and 3 is a line through origin. You can always pause the video, answer these questions, and then look into my suggestions. Now let's solve them one by one. The first question, where we want to find the invariant points of the transformation over the given matrix. So let's write down the matrix and we'll consider the point xy. So to find the invariant point, we'll write the matrix which is A0, 0 minus A, and we'll take a general point xy. So when you do this multiplication, what you get is AX, and in denominator you get minus AY. Now for this to be invariant means you get the same point as x and y after the transformation, correct? So what we are trying to say here is that the image is same as the original. Once that happens, then we have an invariant point. Clear? So that's the whole concept. So if that is true, in that case we should have AX equals to x and minus AY equals to y. So minus AY equals to y is possible only if y equals to 0, correct? And here AX equals to x is possible only if x equals to 0, correct? And therefore we get our invariant point is the origin itself, which is 0, 0. You also understand that for any linear transformation 0, 0, the origin is always an invariant point, correct? Well, that is our answer for the first question. The second question here is, find the equation of invariant lines for the following transformations in the xy plane. A. Reflection on the line y equals to minus x. B. Enlargement centered at origin with scale factor of k, where k is greater than 0. Also, k is not equal to 1. In that case, there is no enlargement, right? C. A stretch parallel to y-axis of the scale factor of k, where k is greater than 1 and k is not equal to k is greater than 0 and k is not equal to 1. So I'd like you to pause the video and provide solutions for this And the solution should include both geometric as well as algebraic part. Please note that in this case, we have not given you the transformation matrix, so you'll have to also find the transformation matrix, then the image, and then get your invariant lines. So you can pause the video, answer this question, and then look into my suggestions. Find the equation of invariant lines for the following transformations in the xy plane. So we are considering R2. First one is reflection on the line y equals to minus x. So in this part, I like to give you geometric interpretation, right? So let's look into geometric interpretation. Okay, so in this part, we'll give you geometric reasoning. For part A, let's try to sketch the line y equals to minus x. So when I say that the line is y equals to minus x, that means it is a diagonal going downwards, correct? So in this xy plane, we have this line which is y equals to minus x. So we're considering part A. Reflection on this particular line. So which are the invariant points? Well, if I have a line which coincides with it, then every point will be reflected onto itself. It is not going to move, right? So definitely we have this particular line which is an invariant line, right? So one of the solutions is that the line which is y equals to minus x is invariant. Perfect. Now here the points are not moving, right? So we have invariant points here. Now, if I consider a line which is perpendicular to this, for example, a line which is like this. So if there all these lines which are perpendicular, what happens to the points on these lines? You will notice that any point on this particular line, when reflected, will be reflected on the line, right? So if there's a point here, it is going to reflect on the line. Does make sense to you, right? So the points will reflect on the line itself. Points are not invariant, but the line is invariant. Perfect. The line is invariant, and therefore we have all these lines whose equation will be y equals to minus x plus the constant c, where c is your y-intercept. Is that clear to you? So those are the lines which are invariant. Perfect. So we have two answers for part A. Is that clear to you? Perfect. Now let's move on and see what do we understand for part B and C. In part B, we are talking about enlargement centered at origin with scale factor of k, right? So we are talking about now enlargement. Centered at origin, right? So now, if I consider this particular case, let me just draw it here. In that case, any line which is going through the origin, right? Let's consider a line going through the origin, right? So in that case, if I multiply a point on this line, it gets onto itself, right? Because the equation of this line is y equals to mx, right? So if I take a point where I have a scale factor of k, that means a point on the line will actually multiply both x and y value by k, right? So a point which is x, y will actually become ax, ay, right? So both get multiplied by a, so the point will remain on the line itself. Does it make sense to you? Now, since the points will be reflected on the line itself, we notice that we will get an invariant line. Perfect. So that becomes our answer for this given situation. So all the lines going through origin, so of the form y equals to mx, will be invariant line in this particular case. Clear? Now in part C, we'll talk about stretch parallel to y-axis. What does that mean? Now y-axis is vertical, so what we're trying to do here is, if we have a point, let us say we have a point x, y in general. So stretch vertical parallel to y-axis means this point will be pushed upwards, right? Stretch parallel to y-axis. This is parallel to y-axis, correct? So in this case, the x value remains same, but the y value gets multiplied by k. Well, sometimes we do write k not equal to 1, since there is no stretch, right? But strictly speaking, we need not write it. Even if k is 1, the point remains where it is. It doesn't, all the points are invariant, right? In that case. Perfect. Okay, so k not equal to 1 is kind of important to write because we are moving the points. So in both these conditions, let me write k not equal to 1, because in that case all lines will be invariant. There is no transformation taking place, correct? So k not equals to 1 could be an important condition here. Okay, now if that is the case, what do you think are the lines which are invariant? So it makes sense that we are actually multiplying the y value. So if the y value is 0 itself, that means all these points here, these are invariant, right? They are not moving upwards, since k times 0 is 0, right? So one line is definitely the x-axis, which is y equals to 0. Right? So that is definitely, we have invariant points, correct? So we have invariant points. No point is moving. The line is also invariant in this case. Now the other will be all the lines which are vertical. So if I have a vertical line, right, so in that case what happens? In that case, any point on the line will actually get its image also on the line, correct? So that also gives us the value of invariance. So x equals to a constant c will be a vertical line, and all these x equals to c means these vertical lines will be invariant lines for this kind of transformation. Is that clear to you? So I think that clearly explains how question number 2 can be done geometrically, right? Now, let us also make an attempt to explain the same concepts algebraically using the multiplication of our matrix. So let's take it on a fresh page now. Now let us look into question number 2 and find the equation of invariant lines algebraically using transformations. So once again, the question here is, find the equation of invariant lines for the following transformations in the xy plane. Now let's consider part A, which is reflection on the line y equals to minus x. So let me sketch this here and draw the scenario to explain how do we find the transformation matrix. we are given reflection on the line y equals to minus x. That means the line will be kind of like this, right? This is the line y equals to minus x. Now to get the transformations, we'll consider 2 points, and these 2 points, as we have always taken, will be, this is 1, 0, and the other point here is 0, 1. When you reflect these points on the line, what do you get? So this point gets reflected, and we get a point, the image of this as 0, minus 1, and the image of the other point is minus 1, 0. And therefore, we can write down a transformation matrix. So in this case, let A be the transformation matrix. It can be defined as 0, minus 1, minus 1, 0. Correct? So that is how we get our transformation matrix. Now, we are talking about invariant lines. So a line can be represented by the equation y equals to mx plus c, where c is the y-intercept. Now, whenever you're working in the matrix transformations, we look into the parametric form. So, if x equals to t, in that case, y is equals to mt plus c, correct? So that becomes the parametric form of our equation. And therefore, we are looking into the image, which will now be, when this transformation is applied on this, which is t mt plus c, what you get here is a minus of, so 0 times t is 0, minus 1 times this. You get minus mt minus c, and in the y this is minus t, correct? So that's what you get. So when you multiply this with the given matrix. Now, if we're talking about invariant points, in that case we get 2 equations here, and the 2 equations are x is equals to this and y is equals to that, correct? So that gives you the condition that x is equals to minus mt minus c, and we could actually write this as bringing mt here, we get mt, we'll just reorganize, okay, and bringing x here, so we get minus x minus c, and t will be equal to minus x over m, and that is minus c over m. So that is the value of t. Now, if you look into the other part, y should be equal to minus t, right? So the other part here is, let's take it on this side, which is basically, let me write here, y equals to t. Now, since t is, that is, it is equals to minus x over m, y is minus t, right? So y is minus t, so the signs will change, right? So plus c over m. So that becomes the value of y in this particular case, right? Now, for an invariant line, we should have the same line, right? So the same slope and same y-intercept. So we are saying invariant. So that means we have again 2 equations to work with. So the slope should be equal to 1 over m, right? Slope should be same. The slope is 1 over m in this case. So slope is 1 over m. That means m square equals to 1, or m equals to plus minus 1. Clear? So that becomes the slope. So we get the 2 values of m as plus minus 1. And now let's equate the y-intercepts. The y-intercept c should be equals to c over m. And if m is equal to 1, so for m equals to 1, let's suppose m is 1. So if m equals to 1, c equals to c. So that is always valid. Is that clear? So we get if M is 1, then C is C. So that means the line y equals to x plus c is an invariant line, right? So that gives us an equation y equals to x, because M is 1, plus c, right? So that is one invariant line. Good. Now, let us consider the case when M is equal to minus 1. So if M is equals to minus 1, in that case C equals to C over minus 1, and that is possible only for C equals to 0. And therefore, the other line which is correct is where M equals to minus 1, which is y equals to minus x. And therefore, we have these two invariant lines for the first case. So our answer here is y equals to minus x and y equals to x plus c are the two invariant lines for condition A. So I hope that is absolutely clear. So in this particular example, we have seen how first we need to find the transformation matrix which could reflect the points on the line y equals to minus x. Once you find the transformation matrix, then you have to apply the transformation to a line in parametric form. Then the image should fall on the line, and therefore we equated the equation equating the slopes and the y-intercepts, getting two different conditions, and we got exactly the same answer as we got in our geometric interpretation. So once again, if you look at it, so here we have our solution y equals to minus x was the line which was symmetric on itself, right? So since it is same points, they are not reflected, so every point is invariant, and the lines which are perpendicular to it are also so perpendicular lines will have a slope of plus x, I'm sorry, so good we took it up. So all these lines will have slope, perpendicular lines will be slope of plus x. So y equals to x plus c and y equals to minus x are the equations of the lines which are parallel, right? So good we saw it back, and then so that is the slope perpendicular to this line. Perfect. So let's move on and take part B now, which is enlargement. So in this particular case, we are talking about enlargement centered at origin with the scale factor of k. So let's get back to our diagram, and we'll first write down the transformation matrix, and we'll also put the condition that k is not equal to 1, right? If k is equal to 1, there is no enlargement. Perfect. So k not equal to 1 is a condition for both part B and C. So once again, we'll take our test points, which are 1 and 0, and this is 0 and 1. So enlargement centered at origin by a scale factor k. That means on both the sides it is enlarged, right? So it gets multiplied, so it moves here, and that also moves outwards, and the scale factor is k. So the points which you get after enlargement will be the x value will change to k, the y value remains 0 in this case. However, here the 0 times k will be 0, and the y value will become k, correct? And so we get our transformation matrix. Let's call this matrix as B. So the transformation matrix will be k0 and 0k, right? So that's how we get our transformation matrix. We're talking about a line which is y equals to mx plus b. Whenever we want to apply the transformations, we take the parametric form. So if x equals to t, in that case y equals to mt plus, we wrote b, let's go with b, okay. So we get mt plus b. Y-intercept you could write as a, b, c, or any letter for that matter. B and c are normally taken, okay. So in our case, when you apply the transformation, what do we get? The transformation matrix is k0, 0k, and the parametric equation is t mt plus b, and you get kt, okay, and here you get mkt plus kb, right? So that's what you get. Now comparing it with y equals to mx plus b, let's first write down the two equations which we get from here. So from here we get the x value as equals to kt, and that means that t can be written as x over k. The y value is mkt plus kb, and substituting t we get y equals to m k, and t is k over x over k, right? So x over k plus here we get kb. So we get y as equal to k and k cancel, right? So we get y equals to mx plus kb. So that's what we get. Now for this we have two conditions, and let's take this equation on the right side. So we have y equals to mx plus kb. So if you compare the slope m equals to m, right, so that is true for all m, and for the y-intercept we get kb equals to b, and this is only true for k equals to 1 or b equals to 0. So that means b equals to 0. Is that clear to you? So that means b equals to 0. And therefore, putting these two conditions here, m could be any value, but b is 0. So y equals to mx is the invariant equation of the line. So all the lines y equals to mx will be invariant. Perfect. So that is what we also got when we did geometrically, that y equals to mx are the invariant lines when we are considering enlargement centered at origin. Perfect. So I hope the concepts are absolutely clear, right? Now let us take part C. Here is solution to part C of question number 2. Find the equation of invariant lines for the following transformations in the xy plane. Part C is a stretch parallel to the y-axis of scale factor k is greater than 0 and not equal to 1. If it is 1, then there is no stretch at all, right? So let's consider this to get the transformation matrix. When we are saying that stretch parallel to y-axis, that means we are stretching in this particular direction. And if you do that, what happens to any point? Well, let's consider two of our critical points which we always take. So the points are 1, 0 and 0, 1, right? So let's say these are the 2 points. So if you stretch them vertically by a factor of k, then this point will, what will happen? K times, because that k stretch is only on the y value, right? So this point actually remains here itself, because k times 0 is 0, right? On the other hand, this point, the x value remains same, but the y value gets stretched. So we get this point as 0k. Is that clear to you? Perfect. So we have a transformation matrix. Let's call this matrix as C. And the transformation matrix in this case will be 1, 0, since that didn't change, right? And 0k. So this is with the scale factor k vertical stretch, right? So that is a vertical stretch. By factor of k. Clear? So obviously k is not equal to 1, otherwise there is no stretch. Now once we apply this transformation to our line, and the line is y equals to mx plus b, where in parametric form, if I write x equals to t, then y equals to mt plus b, right? And writing the transformation, it becomes 100k times the matrix t mt plus b, which is, when you multiply, you get t here, and this you get kmt plus kb. Right? That is what you get. Now that gives you two equations to work with. The first equation is that x is equal to t, and the second one is that y is equals to kmt plus kb. Right? Substituting x equals to t here, what do we get? We get our equation, which is y equals to kmx plus kb. kb. Now, we need to find equation of the lines which are invariant. So for invariant lines, we should have same slope and same y-intercept as we did earlier, right? So same slope means that slope m is equals to km. Slope m is equals to km, and that is possible since k is not equal to 0, it is greater than 1. That is possible when m equals to 0. Correct? So the slope will be 0 in this case. As far as the y-intercept is concerned, right, bk, so bk equals to b will be bk, right? So bk equals to b is possible when b equals to 0. So what you notice here is that when b is equals to 0, then we have a slope which is, so m equals to 0 and b equals to 0 will be the second condition. Correct? Okay. Now, if m is 0, in that case, what do we get? We get y equals to 0, right? So if I put these conditions, then y equals to m is 0. So right, y equals to, we are looking into y equals to mx plus b. So we get a condition that y equals to 0. Now y equals to 0 becomes invariant, where the points are also not moving, correct? Where the points are not moving at all. So vertically, every point on the x-axis remains there itself. So that becomes a part of our solution. Correct? Right? Now, what you also notice in this particular case, that since we're talking about vertical stretch, and we note that any vertical line, if you have a point here, it gets stretched to, and you get to the same value. Now, since the slope is undefined and we cannot really write down the slope equation in the form of y equals to mx plus b, we directly do not get the result from here. Perfect. But you notice that we could have the condition y equals to b. So, x equals to b. If x is equal to b, here is that since we have these two conditions, m equals to 0 and b equals to 0, so in that case, what you can really see here is that if these are m equals to 0 and b equals to 0, in that case, x equals to t becomes the equation of the invariant line, right? So x could be any value t. You cannot normally use the line y equals to mx plus b for vertical lines since they have undefined slope, right? But when you're saying that all these are zeros, in that case, let's consider x equals to t as a condition. Any vertical line, the points will be reflected on the line itself. And therefore, x equals to t will become a vertical line which will be invariant for a stretch which is parallel to y-axis. Perfect. So with that, we explain how we get all the lines which are x-axis and all the vertical lines which will be invariant lines. Now here is the last question, which is question number 3. Find the equation of any invariant line through the origin of the transformation whose matrix is A equals to 3, 2, minus 1, 0. So we are now talking about equation of any invariant line, if any, through origin. So that means line of the form of y equals to mx, correct? So in that case, in parametric equation, if x equals to t, in that case, y equals to mt, right? Now we are given the transformation matrix, which is 3, minus 1, 2, 0. Applying this transformation on the parametric form, which is tmt, what do we get? So from here, what we get here is basically 3t plus 2mt, and we get minus t, right? That's what we get. Now, for the invariant lines, we can now equate that the x value should be equals to 3t plus 2mt, and the y value will be minus t, correct? So we get x and y values from this particular image after applying the transformation. So let's work on this. We have x equals to 3t, we'll take t common, right? 3 plus 2m, and we'll take t common. So from here we can write t over 3 plus 2m is basically equals to t. Y is equals to minus of t, so we get y equals to negative of x over 3 plus 2m. Correct? Now for invariant line, slope should be same, right? So same slope for invariant line. Correct? So we'll equate the slope and find the value of m, which can give us the solution. So what we get here is that m is equals to minus 1 over 3 plus 2m. Cross multiply, so we get 3m plus 2m square equals to minus m. Bring them together, we get 2m square plus 3m plus 1 equals to 0. So we're looking for product of 2 and sum of 3. So we could split this as 2m plus m plus 1 equals to 0. Taking 2m common, we get m plus 1 plus m plus 1 equals to 0. And that gives us a factored form, m plus 1 times 2m plus 1 equals to 0. So with that, we actually get two conditions, right? So we get two conditions that m equals to minus 1 or m equals to half. Correct? We get two different conditions. So for these conditions, we can write down the equation of the invariant line. So we can say that the invariant line are y equals to minus x and y equals to half x. So these are the lines which will be invariant for the given transformation. Perfect. So that is how we can find invariant lines through the origin. So I hope that makes sense. So with that, we come to an end of our test paper. I hope you have understood all the solutions. Feel free to write a comment, share your views, and if you like and subscribe to my videos, that'd be very great. Thanks for your time and all the best.